Welcome everyone. So today I'm going to introduce you to hyperspectral imaging for open pit mining applications, and my name is Friederike Koerting. I worked at this topic or in this topic for my PhD for quite some time, and I now changed to work for HySpex VNIR, which is a scientific grade hyperspectral camera developer. So we're going to look at the topic of hyperspectral and the implementation of that in mining, and which systems do we need to actually do that. As I said, we're going to look into the potential benefits of using hyperspectral within mining. I'm going to give you an introduction to hyperspectral, the method, the approaches, data acquisition, and the analysis. And then we're going to look into different case studies where I used hyperspectral for detection within copper, iron, nickel, and lithium deposits. I'm proposing a new approach here within mining and a new method within mining, because we have seen that a sustainable approach in mining cannot be based on the reduction of extraction, but it has to be based on developing new technologies to create a safer, highly efficient extraction, sorting, and recycling process. And to underline that, I'm showing you the rising demand of different technology minerals here, or clean energy technology minerals, from 2020 to 2040 for different scenarios. And for the scenario that meets the Paris Agreement goals, the SDS here, we actually can see that the share of clean energy technologies in the total demand of the different minerals will grow significantly. For copper, that's an increase of 40% from 2020. For rare earth elements, that's similar. For nickel and cobalt, we have an increase of 60 to 70%. And when we look at lithium, we actually have an increase of up to 90%. And this is based on the rise in demand for electrical vehicles as well as the battery storage. And this is going to be the largest end user of lithium in 2040, same with nickel and also copper. So how would we implement hyperspectral in the mining environment? And we're looking at different scales here. So for an exploration scale or a monitoring scale of very large open pit operations or exploration of large areas, we can look at satellite-based sensing or airplane, so airborne sensing. When we look at an active mining monitoring for modeling or increasing the accuracy of the different ore models, we look at an approach which will be powered by UAV, possibly because of security reasons, but maybe also by a tripod-based system. Then we have the whole area of sensor-based sorting. So here, as an example, conveyor-based sorting or monitoring approach, which is closer scale, so we have a closer distance between our camera and our target. And then we're looking at mine face scanning or close to face scanning, and also different sampling approaches. And for the very near scale sampling, we have either different samples in the laboratory, we have drill chips, or it's been used quite often now for drill cores and the digitalization of drill cores. And here we're looking at mineralogy and mineral mapping. For a mine face scanning, I'm going to concentrate on this whole mine face scanning approach, which can be done by a tripod or also by a drone or UAV. For these, we have different requirements and considerations to actually implement it in an open pit mining environment. We have a very rugged terrain, a harsh environment, which means that we have to have sensors which reflect that, and they can be used in the rugged terrain, talking about dust, heat, but also the operator's going to wear PTE, which means they're not going to be super gentle with the material. The same goes for handling. So in terms of size, weight, and complexity, it has to be easy to handle, it has to be easy to handle with PTE. And then we have a high turnover rate, which is asked for. So processing and mapping have to be high speed, and they have to be integrated seamlessly into different approaches and processing aspects in the mining flowsheet and in the open pit flowsheet. And depending on that, we will need the right sensor and the right camera to work with it. And this will depend on the deposit type and also the needed level of material distinction, the heterogeneity of the deposit, stuff like that. Looking at the full life of mine value chain, solar optical spectroscopy, in this case hyperspectral spectroscopy, can reap different benefits in the different stages. I just want to underline that here. So we're looking at an implementation or the usage of hyperspectral in the discovery phase. We can use it for smart selective mining within bulk online analysis and ore sorting or monitoring, as well as the stockpile management and within the processing chain as a means of quality insurance. And you can see that by, for example, targeting different areas by satellite or airborne remote sensing, you can save cost in discovery in terms of high drill core costs or high drilling costs by targeting specific areas within your area of interest. And then we can increase the run-of-mine rate, which in turns also leads to a reduction of energy consumption in the processing and an increased productivity. And I want to highlight this by showing the different positions within the open pit or mining flow sheet. So hyperspectral sensors can be used for a monitoring and a characterization of the material, mainly for a low-grade ore elimination. So we're looking at a pre-concentration, which can happen at the mine phase. It can happen by looking at tailings and the remining and reclaiming of tailings. And it can also we can look at different stockpiles and the stockpile management here. This pre-concentration would infer an increased ore grade, a decreased input into our processing, a smaller tailing output in the end, and an upgrade of the run of mine. We're looking at the possibility to divert different materials into different process lines, so diverting them pretty early within the processing and separating different ore qualities or helping with an accurate blending for the processing. And then we can actually look at it in the different processing steps as a quality management and quality characterization of the different products in between processing steps. The sensor-based sorting in general, which does not only include hyperspectral but different aspects, is widely applicable, but it hasn't been picked up by the raw materials industry as much. It's been picked up by the diamond industry and also the industrial materials, but we're still looking at an implementation, for example, in iron ore characterization. It is suited for coarse particle separation, where the liberation is insufficient to achieve a high or a final concentration. And it can be used for the size of blasted fragments, cuttings, or also crushed materials. And it is basically filling the gap from the mine to the mill, but you can see that even then we have the possibility to have a process monitoring or conveyor belt monitoring here. In the different case studies that I'm going to show you, I'm concentrating on the area of the run of mine, run of dump here. So in this position in the flow sheet where we have a close to phase identification. Just want to clarify that this is only possible if we have heterogeneous ore with macroscopic blocks without a very gradual transition between ore and waste. And also additionally, we actually have to be able to mine selectively. So if we have too large shovel sizes or the equipment is too large to actually mine selectively, we're not going to be able to harness the power of this hyperspectral distinction of the material. In those cases, we would, for example, look at the material that goes into blending so that we have a more effective blending instead of having an extractive selection here. We're now going into the basics of hyperspectral, and I'm going to give you an introduction into different platforms and instruments with different spectral resolutions, some basics of solar optical spectral remote sensing, and also a little list of the different active VNIR-SWIR active minerals. As I said, I'm working for HySpex, and we are a camera developer, so we're also going to look into the different qualities that we want in our hyperspectral cameras. Just to give you a general idea, there are different hyperspectral platforms and spectral and spatial resolutions that we expect from the different platforms. Just so you've seen those in the beginning of this presentation, we have the lab setting where we have very high spatial resolution and very high spectral resolution. We can use scientific grade sensors in that case. Then we have the tripod setting and also the UAV or UAS setting, where we look at larger areas, and that means that our spatial resolution, so the pixel size, is going to vary depending on the distance from our sensor to our target. So there can be sub-centimeter, but usually it's sub-decimeter or even meter pixel size. And we still have a very high spectral resolution here, at least with the hyperspectral instruments from HySpex. And then we have the stage of airborne sensors and airborne cameras and also satellites. And for airborne, you can still use hyperspectral sensors. And for satellites, there's also some hyperspectral satellites out there that the data can be used for different projects. But usually satellites are more in the multispectral or superspectral range, which means the spectral resolution varies and the spectral band number and width is very different to what we expect in hyperspectral. This already brings me to an introduction to the different spectral resolutions for different optical remote sensing systems. So we're mainly talking about hyperspectral, superspectral, and multispectral. And those differ in terms of band number, in terms of band position, and the wavelength region that they cover, and also the bandwidth. And you can see we're talking here about the visible to near infrared and the shortwave infrared. So from 400 to 1000 nanometers and from 1000 to 2500 nanometers. The hyperspectral sensor actually collects within this wavelength region in a large number of narrow consecutive bands, which means it's able to identify and resolve very fine spectral features in those areas. When we look at superspectral, and this is an example for the WorldView 3 commercial satellite, this is the band setup, you can see that it's still covering large areas of the spectrum, but missing some areas here where we have atmospheric influence, so there are no atmospheric bands here. And you can see that still we have very large spectral bands, but we're still able to cover a large portion of the spectrum. And when we're looking at the multispectral, this is the example or the band setup from Sentinel Copernicus 2. Sentinel 2 Copernicus. You can see that we have a focus on the sphere, on the VNIR region here, and then we only have a couple of bands in the sphere region. And just to show you what that looks like in terms of the spectral fingerprint, this is from the same material. So we're looking at the multispectral here in green, the superspectral in yellow again, and then the hyperspectral in blue. And you can see that only the hyperspectral is able to identify very fine features here in the atmospheric windows. And then again, for example, this feature, which is a very typical ALH feature for clay, for kaolinite. And this is going to be important when we want to differentiate between different minerals and also between different lithologies. We now talked about different application domains and different platforms, and when it comes to the choice of the right instrument and platform, there are different aspects for the operation that have different priority. For example, for UAV or tripod, you would be interested in the ground resolution or the pixel size in terms of mining, for example, because of the spatial variety within your deposit, and you want to be able to resolve that. But even when we look at these specific demands, there's one thing that we cannot compromise, and this is the spectral fidelity, and we're going to go into that a little bit more. So when we talk about spectral fidelity, we are talking about hyperspectral imagery key quality parameters. This is the point spread function, the PSF, the Keystone, and the SMILE. And all of these arise from the design of the push broom instrument. So it is dependent on the actual hardware that you're looking at. And we want to concentrate on that a little bit. So for the point spread function, when you use a monochromatic source, for example, a laser, you would expect it to heat only one pixel here in the spatial direction. And this would happen in the perfect world. But as we can see, the real world actually gives us some problems here. And in the real world, that is never the case. We never hit only one pixel in the spatial dimension. And this is also wavelength dependent. And there were some independent reports on that. And this is a comparison of the HySpex camera and a competitor camera. And I just want to show you that HySpex has put a lot of effort into being the closest as possible to the perfect world, which means hitting just one spectral pixel and actually having this distinction between different spectral pixels. Just to give you an idea what that would look like, in an imperfect PSF, in an image introduces something like a blur in an RGB image, but here we are talking about a spectral blur. The next parameter is the keystone, which can be much worse because it brings about a non-linear mixing. The keystone effect is what you would often see in normal RGB images when they are taken from a specific perspective. And this results in this distortion here. And we can actually correct this distortion in RGB images with Photoshop magic, but it's not possible to do that in hyperspectral imagery. And sometimes the keystone is actually larger than 30% of the pixel, depending on the instrument that you're looking at. To give you an idea what that looks like, so if you imagine two minerals here in red and in blue, and we want to look at the edge between these minerals, so the grain size boundary, or the alteration zone between that. If you analyze the spectrum on such an interface with a keystone present, here shown with the red line, you will end up with a mineral of an unknown type, for example here, because it's not going to be able to identify this very sharp border or grain size between the pixels, but because of the geometrical distortion here, we're going to collect signal from the blue as well as from the red mineral. And this introduces this unknown type, which is a non-physical object just brought about by spectral mixing from the keystone. And when you're looking at geological features and the different scales that we're looking at, we're going to have problems when they are going to be very close to our pixel size, and the pixel size can be tens of centimeters when we're looking at UAV. And this is just showing you how this differs between a 10% keystone to a 30% keystone to a 75% keystone. And we're looking at an object which is 5 by 5 pixel and objects that are 1 by 1 pixel. And you can see that for a keystone of 10%, we are still able to identify this 1 by 1 pixel pretty well. And with increasing keystone, we're not going to be able to identify the 1 by 1 pixel anymore. We have to look at areas which are 3 by 3 or 4 by 4 pixels to actually identify that correctly. And that's going to be a problem when our pixel size is 10 centimeters and we're looking at an outcrop, for example. Now we're going into the basics of the spectroscopy, and I wanted to show you this graph again and this reflectance spectrum, which we've shown before and seen before. Just to talk you through this graph a little bit, we have the wavelength here on the x-axis from 400 to 2500 nanometer, the visible near-infrared to the shortwave infrared here, and then a reflectance which is scaled here from 0 to 10,000, so we have around 60% of reflectance of this material when we look at that. And we actually look at these absorption features and the position of this absorption feature, in this case, this example. So the position of this absorption feature tells us something about the material or the element in that case. So this is used for an identification. And when we look at the depth of this absorption feature or the width of this absorption feature, this can be used as a semi-quantification. Just to show you a little bit the difference between what causes the absorption features in the VNIR and in the sphere. So in the VNIR, you can see here we have actually the element depicted or the element associated with the absorption feature. Here we're talking about element transitions, so energy from the light source causes energy changes, which results in the transition of ions in the atom, and this is causing the absorption feature. So here we're looking at metal ions mostly, and in the shortwave infrared here we're looking at molecular bonds and the changes introduced to these molecular bonds by incoming energy, and the vibration, for example, is causing the absorption feature here. Apart from just the chemistry and the physics, so the molecular changes in bonds, introducing changes in the spectrum there's other different factors which influence the spectrum. We have to keep them in mind when we're looking at different scales from laboratory to the outcrop to UAV. So the particle size can change the spectrum. Then we have mineral mixtures, which will change the spectrum quite tremendously. The view geometry can introduce some changes, as well as surface roughness, of course surface coatings, because we're only seeing the surface, and water content within the material. And then we have to keep in mind that there will be some strong changes of the absorption features in the outcrop scale, mainly because we're introducing atmosphere between our camera to our sensor, and this is a lab spectrum here. I just wanted to show you for which non-fuel mineral commodities hyperspectral is theoretically possible or has already been introduced. And this is the non-fuel mineral production based on the USGS. Be careful, this is not a log scale, otherwise the sand and gravel would just blast our graph out of proportions here. And I wanted to show you that for most of these non-fuel minerals or raw materials, hyperspectral is actually a viable option, and there are deterministic absorption features which can be used to identify, for example, different phosphate rocks, different iron ores, or different carbonate clay mixtures in the case of cement. Now we're going into the different hyperspectral studies and the activity of the different mineral types and mineral groups in the VNIR and the shortwave infrared. I talked about carbonates just now, so actually for the non-silicates, carbonate, hydroxide, and sulfates have deterministic absorption features in the sphere. The same goes for oxides, which have the absorption features in the VNIR. When we look into the silicates, there are quite a few deterministic features that we can find in the shortwave infrared. And I've highlighted the filler silicates here because those are very typical for the different alteration zones of, for example, copper deposits. And I just want to highlight also that, as you can see here, the different sulfides are not very well distinguishable, or even are not being able to see with hyperspectral because we don't have any absorption features in the spectra, which means that we have to rely on different alteration zones, which can be identified, for example, in the shortwave infrared. For different studies and hyperspectral studies done on different ore deposits, I can just introduce you to the Bellini paper here from 2017, which is a review paper showing the different how well different ore deposit types have been studied by hyperspectral. And I tried to highlight here in a bit stronger red that there have been several studies, or even large number of studies, for example, for magmatic deposits, for rare earth especially, and for porphyry copper in the hydrothermal, as well as for different gold type deposits. And then for deposits which are, for example, important for nickel or for cobalt, and aluminium, laterite and bauxite only had a limited number of studies here, which means there's also a diversity of knowledge between the different deposits and the hyperspectral fingerprints that we would expect here. Yes. Now we're going into the hyperspectral data acquisition types, and also a little overview about how hyperspectral analysis and how the workflow is going to look like. Starting with the laboratory data acquisition and the setup, we have our two sensors mounted here. This is the VNIR and the SWIR sensor, so covering the range from 400 to 2500 nanometers. Both of them are line scanners, which means they measure one line and the image is built line by line. So in the laboratory setup, we have a translation stage where the samples are placed, and this is moved line by line underneath the sensor to build up the whole image. And you can see that we can play around with different light sources and different angles of the light source as well. This is the setup at the German Research Center for Geosciences, where I also did my PhD. And I just wanted to highlight that for these kind of samples, we can use all kind of samples, but the sample preparation is minimal, so they can be left in their natural state. And as we want to compare them with an outdoor setting, they should be left in the natural state with all of the variety that we can see here. For example, we have different shadow effects, and we have different grain sizes, and we have also different albedos within the image, and then we have material in the image which might not be the same material as the material sampled next to it. And the second scale would be a tripod setup, where these line scanners are mounted on top of a tripod on a rotation stage, and instead of moving the sensor line by line, this is moved in a rotational manner. So here we have a rotation of the sensor which collects the image line by line based on this rotation. And this is the Aplikimine, which is a copper gold pyrite mine in the Republic of Cyprus. And here you can see that our sensor was placed around 100 to 150 meters from the mine face, depending on where on the mine face you're looking. And this results in pixel sizes of roughly 15 to maybe 3 to 4 centimeters of pixel size, depending how close the sensor is to this object here. This is a different tripod field data acquisition example from the Bajoca mine, which is a lithium-bearing pegmatite mine in Portugal. And this was done also with a German research center and the LIGHTS project. And I'm going to give you an intro to this mine later on. And then we have our UAV data acquisition with the HySpex VNIR in that case. And you can see some sample data here and a mock-up of how this UAV analysis or UAV data acquisition actually looks like. And when we look at the data analysis workflow, and I'm going to go through this very briefly, when we've ticked off the data acquisition, we're looking at data processing prior to analysis. And this includes a reflectance retrieval, this includes the reduction of scattering effects or the smoothing of the spectrum, or even the downsampling, depending on which spectral resolution do we want from this image. And after that, we actually have our analysis. And for this analysis, we need some preparation, but that depends on the analysis type. So we have a knowledge-based analysis, we have a data-driven analysis, and then we have a hybrid of both, just to name the broad groups of that. And the knowledge-based approach, the name suggests that this relies on the knowledge of the expected spectral behavior. We're talking about feature characteristics here. So we're looking for very specific absorption features in the spectrum. And this depends on our feature extraction or feature modeling. So we need to have the feature modeling before we can do this analysis. For the data-driven approach, we can distinguish between a comparison-based and a training-based approach. And this just means that we need reference data to let our algorithm know what we're looking for. And this can be done by labeling training data or by collecting end-member sets, which would be a spectral library, for example, here. Yes. And I just want to let you know that there are different considerations that you have to be aware of, depending on what kind of data are you collecting, what kind of information in the data are you interested in, what mapping approach or analysis approach is open to you, and you have to consider these different options and find the best approach for you and the best analysis for you. So one thing would be, what do you actually want to learn from the data and how can you validate that? So are you using samples in the laboratory? You want to learn or train your algorithm based on this and then infer it to outcrop data. How can this be inferred? Is this based on data? Is this based on the information in the spectrum, or is this based on spatial correlation in your spectral data in the laboratory? So you have to keep that in mind to make good models on that or base good models on that. And then you can also learn from regions of interest within your data. And this might be helpful when you're just looking at one open pit mine and you have very well-defined areas of high-grade and low-grade ore, and you can learn from that. But you can have problems when you try to infer that to a different mine where the spatial correlation between high-grade and low-grade is not the same, but it might be a part of your model already. And then you can also use spectral libraries to learn from, or spectral libraries to use for comparison-based approaches. And this can be done by using, for example, USGS or CSIRO spectral libraries, or it can be done by sampling on site and building a site-specific spectral library that you can use. And this site-specific spectral library ideally would be validated by geochemistry and mineralogy. And then you also have to keep in mind is what do you actually look for? Is it mineralogy? Are you interested in the different minerals? Are you interested in the lithologies? Are you interested in the grades, so more of a metal content? What kind of samples do you have? So you have to know what you're looking for in your mine or open pit compared to what you're looking at in the laboratory. So are you looking for powdered materials? Are you looking for very well mixed materials? What is the level of detail that you're interested in? What proxy do you need to look for different zones, for example, in an open pit mine? And then you have to be aware that the calibration sample set that you're using is very crucial, especially for learning-based approaches. So the labeled data has to be integer, of integrity. And you have to know if that is inferable to the open pit. Okay, so that being said, we're going into the different case studies, and we're looking into deposit types of copper, iron, nickel, and lithium that I worked with at my time at the German Research Center of Geosciences and the University of Potsdam. We are jumping right into the example of copper here in the Republic of Cyprus, and the Cyprus sulfide deposit belongs to the mafic type of volcanogenic massive sulfides, VMS. The expected mineralization here is of pyrite, chalcopyrite, and sphalerite, with inclusions of galena and secondary copper-bearing minerals. As I already told you, these are not going to be visible in the shortwave infrared and the visible to near infrared. So we're looking for the alteration zones instead. And in Cyprus, the alteration is dominated by silica and chlorite and disseminated pyrite. More precisely, the alteration here is going to be differentiable by being able to map sericite, chlorite, kaolinite, and smectitic alteration zones, for example, or something like that. And we're looking at two open pit mines here. We have the Aplikimine open pit, which was closed in the 1970s. So this is going to be dominated by secondary alteration. And then we have the Three Hills open pit, which is one open pit mine in the operating Skouriotissa mine. Both of them are copper gold pyrite mines. I want to show you different approaches of the analysis, and we talked about knowledge-based and data-based, and I'm going to show you, or data-driven, I'm going to show you these on the example of the Aplikimine. And you can see the Aplikimine here and the open cut, which is in the north of this open pit, and you can see that it is highly weathered, and it will be distinguishable by the different weathering zones here. And from the knowledge-based aspect, we're looking at a very simple aspect, which is the bend ratio approach, which means we know that the bend, the absorption band for clay or for kaolinite is located in the region of 2,160 to 2,200 nanometers, and we're doing a bend ratio there, and then we're looking also at the MgOH absorption feature, which here is important for the occurrence of mica and chloride. And you can see from the clay bend ratio image that we can see that this is concentrating mostly on this open cut, and you can see that we are staying within this alteration zone here in the center, but there's no typical zonation, or there's no main zonation visible here. When we look at the mica and chloride, you can see, again, we are concentrating, or this is concentrated on the open pit here and on the open cut, but you can see that we have some higher areas or alteration visible here in the center. And this is already a very good approach to differentiate between different zones here. So when we look at the data-driven approach, I followed a data reduction first, or an approach of data reduction first. So for this case study, I built a spectral library from samples in the laboratory, and I just wanted to show you the difference between the hyperspectral data and then the reduced data that I used. And here you can see we have the full spectrum, and we can see very fine features in the sphere, but also in the VNIR. And when we look at the reduced data that I used, you can see that I excluded a complete range here between 1,300 and 2,000 nanometers, because this is influenced a lot by the atmosphere. And then we have a sensor which has wider bands in the VNIR, and it has still very sharp bands in the sphere, so we still see these very fine features here. A bit more in detail, you can see that we have 40 nanometer bands in the VNIR. This is the band width, and then 50 nanometer wide bands in the sphere. So we're going to be able to resolve medium strong features in the VNIR and very fine features in the sphere. And I excluded this whole range because when we look at the atmospheric window and the influence of the atmosphere, you can see that this area is highly influenced by the atmosphere. And then in the sphere range, we have an atmospheric window in this area. So we can still see some spectral absorption features in this area. But a lot of it will be covered along those edges with the atmosphere. And I did this data reduction not only to reduce the data size and the noise level, but to make this data more manageable to implement in possible day-to-day activities. And then I wanted to look at the possibility to just look at the analytical features without having this influence of the atmosphere. So for this example, I started with a laboratory-based approach. I sampled my material in the mine. I scanned it in the laboratory, I built a spectral library, and I did a clustering based on the geochemistry of the samples and the mineralogy of those samples, and also the spectral fingerprint of those samples. And this leads to a spectral library, which I will use for the analysis, which is based on 7 different clusters or 6 different clusters when you exclude the gypsum cluster. And you can see these different clusters here in the mapping based on these clusters. And I inferred this to the outcrop, and we will see the classification in the next slide. And you can see that we have a comparison here of our classification and of the expected zonation based on Antivaches mapping in 2015. And from our classification, you can see that here in the center, we have a stronger influence of our chloritic stockwork. And then towards the edges, we can see that we have more influence of the smectitic alteration here in blue. And then on the outer edges, we just see the pillow lava with some influence of different minerals, but mainly pillow lava. And this matches very well with what we expected in the mine phase based on the geological mapping. And also we have these pockets of yellow here, which is evaporate based on the secondary weathering on the surface, and this is actually very copper rich, and we were able to actually pick that up as well within this chloritic stockwork. And this is just to show you how we would show this mine phase scan that I just showed, how this would be represented within a 3D model, so that we can take into account the actual location of the different pixels. And this is also very helpful, for example, when we need this for modeling further in active mining. So another example is the copper-gold pyrite mine Skouriotissa in the Republic of Cyprus. And here the main goal was to differentiate between lower copper grades and higher copper grades. And just to give you the geological setting here, so we have a fault which runs right through this deposit. I tried to show that here in this shaded area, but it actually just like crops out here somewhere, and then it runs into this area. And you can see that this is an east-west running fault. And north of this fault, we expect the lower or medium copper grades, and towards the bottom of the open pit, we expect the higher copper grades. And I mapped here just 3 basic classes, so higher copper grades in pink, the medium copper in red, and then the very low copper grades, more clayish material in yellow. And you can see that the hyperspectral mapping actually reflects this geological setting pretty well. You can see that we have medium grade copper here, then pinkish higher grade copper goes into the depth of the open pit. And then the clay actually pretty nicely follows this fault line by showing the alteration, which is enhanced to this fault line a little bit. Going into iron ore and iron ore samples. So I had a sample set from iron ore mines, 2 different mine sites in Brazil from the Minas Gerais district. And these samples basically enriched ederbarite, intermediate grade ore, and kanga. And the expected iron carriers of hematite, magnetite, and martite. Iron is very much active in the VNIR spectral range as a metal ion, and it's more like the different contaminants that we expect, for example, different clays, are active in the sphere range. And for these samples, we have iron samples from 24% of iron to 68% of iron, so very much contaminated samples as well. And I just want to show you the differences in accuracy of mapping. So I again did a per pixel classification, and I compared 3 different per pixel classifications: the NGeoMap from the German Research Center of Geoscience, the Spectral Angle Mapper, a very classical approach, and then Recents Plus, which is the binary feature fitting from Red Data Spectral Analytics. And when you look at the per pixel classification, you can see that for the different approaches, here we have a feature reconstruction, so that's a hybrid approach. We get an accuracy of mapping of around 53%. Then for an automated comparison-based approach, we get 65% of accuracy of mapping compared to what we expect. And then for the Recents Plus, you can't see that, but that's around 73%. So we have an increase of about 20% between a feature reconstruction and this feature reconstruction. And SEM is comfortably in the middle, but only has an accuracy of 65%. And you can see that it has some issues with material of different albedos. So, for example, for this sample, you can see that it has different albedos and different shadow effects, and the same goes for these samples here, where you can see that there are some differences here, which are picked up by SEM pretty much. And of course, this is not an easy sample set. You can see we have different areas here, which might not be the same material or are just mixed in the material. Then we have very strong shadows, and we have different grain sizes. So based on this very natural state material, we're pretty happy that the Recents Plus algorithm is able to actually pick it apart just based on the spectral analysis. This has nothing to do with spatial correlation or anything. And for stockpile management, I wanted to show you an approach based on satellite imagery. So I used the same spectral library, which is of course not completely accurate, because here we're looking at stockpiles in Australia and Port Hedland. And I just wanted to see how this relative iron content based on these samples that I just showed you is being mapped in the stockpiles. And we have to remember that the Copernicus Sentinel-2 data has a 20-meter resolution, which means we will have mixed pixels, but still we are actually able to pick apart the local material here, so the shoreline, and the stockpiles pretty well, and the stockpiles and also the infrastructure that has to do with the stockpiles, and you can see that in bright red here. Another approach for iron is a tailings monitoring, which means that we can use secondary iron minerals and map them as proxies for acid mine drainage, AMD, or for pH. And I wanted to show you a comparison between a satellite, so this is Sentinel-2, and a superspectral satellite, the commercial WorldView 3 sensor. And this is the VNIR only with 4-meter pixel resolution. And you can see that Copernicus Sentinel-2 is able to find this open pit, which is good. Because it's a very, very small open pit compared to active open pits. So this is Mitsero mine in the Republic of Cyprus. And it shows that we have this mix of clay and iron in a lot of areas, and then we have some hematite and goethite pixels. If we look at the higher pixel resolution and look at the WorldView 3 imagery, we can see that actually this clay and iron can now be distinguished, and we can actually see clay pixels, so illite or muscovite or clay, and we can see hematite and goethite, and we can see a much better distinction of different areas and a much better distinction of different proportions within this mine. So this has something to do with a slightly higher spectral resolution, but mainly because we have pixels that are not mixed as much. Here we have 20-meter pixels, and the material within one 20-meter pixel is mixed, and then we have 4-meter pixels. So yeah, that makes a huge difference for the mapping already. So here we're looking at different laterite samples. So this is a case of lateritic nickel deposit samples from a saprolitic laterite ore, also from Brazil. And those are an important source of nickel, and this is based here in iron ore in the iron ore limonite. So we expect a nickel content of 1 to 2% maybe. And maybe you can see the legend, but I'm just going to show you the differences here. So we have ore which is high in nickel, but also high in contaminants, for example, yellow. And then we have ore which is high in nickel, but has medium to low contaminants. And this would be our go-to here, for example, in green. And then we have also some samples of waste material here in blue and of the surrounding limonite here in purple. And I also just wanted to show you the distinction of different mapping approaches here. So we have the EN GeoMap again from the German Research Center of Geosciences, the Spectral Angle Mapper, and Recens Plus. And I only used VNIR data here, so no SWIR. And I wanted to see, can we still see the differences in contamination? Can we still see the differences in nickel quality based on a spectral library? So again, a comparison-based approach. And you can see that we're going from 70% for EN GeoMap in an accuracy of mapping to 82% for the Recens Plus algorithm from Red Data Spectral Analytics. And you can see that this is able to pick apart the different samples and areas pretty well, same as with the SEM, which has some more effects of shadows here, for example. As an application, I looked at the MOA, or the mining around MOA in Cuba, and this is also lateritic nickel mines. They are deposits located around this area, and you can see that there are some open pits, which are the lighter regions here, and then we have some bedrock here. And I used the same spectral library. Bear with me, because this spectral library is based on samples from Brazil, so we have differences in mineralogy, we will have differences in quality. But just to get a broad overview, and this is again Copernicus Sentinel-2 data from June 2020, and you can see that in these open pits, those differ either that they are medium grade ore, which is to expected because the high grade was extracted already, or we have a more high grade but high contaminant ore in the non-exploited areas here in the bedrock. So even in the Sentinel-2, even with 20 meter pixels, we're able to pick that apart pretty well. And when you think about the worldview or even higher resolution hyperspectral data, we could find very fine distinctions in the ore for extraction here. And the last example is of a lithium-bearing feldspar mine in Portugal, which is from the LIGHTS project from the GFZ, which is the Lightweight Integrated Ground and Airborne Hyperspectral Topological Solutions project. I'm not going to lie, I had to read that. So here we have a pegmatite mine, and this pegmatite is lithium-bearing. And this is in the Almendra region in Portugal, so northern Portugal. You can see the shape of this pegmatite here, and this is a granitic pegmatite, and you can see that this feldspar mine is actually following this pegmatite and mining this pegmatite. And we had 2 minefield scans in the area based on a tripod, and we had some overflights with the UAV. And based on the sampling, which we analyzed in the laboratory and also geochemically, we built a spectral library, and this spectral library is based on the spectral distinctions, based on geochemistry, so again a clustering of the geochemistry, and on different lithological or different lithologies that are already published in the area. And when we look at the overflight here, so careful, now we're looking at north here, and the pegmatite is going from right to left. And we are looking at the overflight here, right at the border between the pegmatite and the surrounding metasediment. And you can see that in this overflight and with the classification, we can actually distinguish this border pretty well. So we can see that here in blue we have the pegmatite, and this is a granitic pegmatite, which has been mined in an open pit. It's not completely fresh, which means it's weathered in varying degrees. And this is shown by these 2 blue groups. So we have kilonitic granite weathering going on here. And then we have the metasediments on the sides. And then here at the edge of this overflight, you can see that that's at the edge of the open pit or the mining activity. We still have the enriched pegmatite and lithium-richer pegmatite here with mica. So, and we're looking at a MineFace scan now, which is located at this border. I'm not sure if you can see it. So we're looking at a MineFace scan, which faced or scanned this area in a rotational movement like this. And this is the MineFace scan. So here we have our scanner, and it's scanned in this direction, just to show you again. And towards the left here we have the pegmatite, and towards the right here we have the metasediments. And you can see that this distinction is very, very clear in the hyperspectral, even though it's not clear in our color infrared. And you can see that, again, the pegmatite is dominated by this weathering and like granitic kaolinite weathering. And here the metasediments in the small scale is actually dominated by the weathering crust on top, which is iron rich. Yeah, and I just wanted to show you these different samples, and with that I'm going to close. I'm already over time, because I'm not going to answer any questions or all questions, let's say it like that. I'm happy for you to contact me via LinkedIn if you're interested in the topic. You can also find some articles there. And I'm happy to answer any questions even after this presentation is done. So here are my details. If you're interested, let me know. And thank you for your attention.